Hello? Hello? Yes? யாரு?
So Sanjay? Yes, sir. Good evening. Good evening. Welcome, sir. Welcome, sir. Good evening. Salraj.
Thank you.
So
Thank
you
you.
can, rights are given to you, sir. You can share your PPTs and you can check it.
Sure.
Yeah. So time 5:35 will start, sir. People are joining. 5:35
Yeah.
people. Yeah.
Sure, sir. Sure. Let me just.
So it is there. Make it put is PPT mode. Make it full, sir. Full screen.
Yeah, yeah. Just 1 second.
Yeah. Right, sir. Now it's okay. Top there is a screen coming, sir. Why on blue board is coming? Why?
Which one?
Yeah, top that area.
Here.
So yeah, where you indicated your arrow,
Yeah.
why is it coming that top letters are not visible?
Actually, it is because of the sharing options are provided there. So, like mute, share video. So I think that section will be cut off.
Okay, check it. It is blocking that letter.
I think now it's.
Now it's okay. Now
It will
still
go off
something.
as soon as.
Yeah. Something. Some more thing. I think the screen should go up still. Now flow 3D is visible. Only weld was visible earlier.
Okay. I think now it's fine, sir.
It's okay, but okay.
Yes.
Right, sir. You can unshare it. 5:35 will shortly start. Okay.
Yes, sure.
We'll wait for few more minutes.
Sure, sir. Sure.
Unshare it so that people will come in the grid. Then we'll start the program. That's all.
Sure, sir. Sure.
Yes, Mr. Sanjay, we will start the program. Okay. Let the other people join. Okay. Sanjay?
Okay, yes, sir.
Shall
Sure.
we start the program?
Yes, yes.
Yeah,
Sure.
yeah. Okay. Just some preliminary is there. Just wait for a few minutes.
Yeah.
Happy good evening to everyone. Today we have an interesting topic, that is Introduction to Flow 3D Weld CFD software is going to be delivered by eminent personality, Mr. Sanjay J, Engineer Technical, Mrs. Kaushik International, Indira Nagar, Bangalore, Karnataka. First of all, we thank Mr. Sanjay for offering to deliver a topic to our members, IEW members, Indian Institute of Welding members, and Institute of Engineers members, other professional bodies situated in BHL campus, 3,000 acres campus. We regularly conduct a weekly program for the past 3 decades without interruption. Actually, in all the 15 disciplines. Today, we are conducting in optimizing welding process, unleashing the power of CFD by Mr. Sanjay. Actually, our aim is to propagate the emerging technologies about whatever is happening around us, and it is reached our members, students, our industry experts, as well as the public at large. This is we are doing our IAW is doing a lot of seminars, symposium. We conduct National Welding Meet 2021, and Institute of Engineers we also conduct regular symposiums, seminars, workshops, and all. And today we conduct about this particular topic. And with this small introduction, I call upon Mr. Lakshmanan, Engineer Lakshmanan, to introduce the speaker to the audience. Over to Engineer Lakshmanan. Lakshmanan is there? Hello? Mr. Lakshmanan?
Hello.
Mr. Lakshmanan, please introduce the speaker to the audience.
Sir,
Mr. Lakshmanan? Yeah, please introduce the speaker, Mr. Sanjay.
Hello.
Mr. Lakshmanan is our former honorary secretary of Institute of Engineers.
Sir, actually, sir, only. Hello. Sir, good evening, sir. Hello. Just a minute.
Sir, KK, sir.
Just a minute, sir.
Sir,
Yes, sir.
proceed,
Lakshmanan, please go ahead.
Please, just a
You're
minute.
not audible.
Sir, please, just a minute, sir. Just a minute. I'm taking this.
Lakshmanan?
Sir, please.
Yeah, kindly unmute your mic and please introduce.
Sir, okay, sir. Please, just a minute. Mr. Sanjay, engineer. Hello. Technical support. MS Kaushik International. Indira Nagar, Bangalore 38, Karnataka. Welcome, sir.
Thank you, Mr. Lakshmanan. Thank you.
Okay, sir.
Now over to Mr. Sanjay, sir, for your presentation, sir, please.
Bachelor's degree in mechanical engineering, and I have been assisted Kaushik International for last 2 years. Kaushik International is an esteemed associate of fellow Flow Space Inc. USA has established an impressive legacy spanning 2 decades, focusing on computational fluid dynamics, CFD software in various industries and academic industries. The software has helped numerous industries by providing powerful simulation capabilities across a diverse range of applications and industries. Kaushik International entrusted with the task of working on CFD simulation software, a role that enables to contribute to various sectors and industries such as welding, additive manufacturing, metal casting, civil engineering, through the utilization of this advanced software, highlight the relevance of simulation software in these specific domains, showcasing how it can streamline processes, optimize parameters, and mitigate tasks, mitigate risks, and also help organizations optimize their designs and gain invaluable insights into their process by leveraging the power of simulation, enable engineers and industries professionals to make informed decisions, enhance efficiency, and ensure the successful realization of the projects. With this brief introduction, I request today's speaker to take that forum for delivering his lecture.
Okay, thank you, Ms. Lakshmana. Now the platform is over to Mr. Sanjay, please.
Yes.
Start your presentations.
Yes. Thank you very much, Mr. Lakshmanan and Mr. Selvaraj, for giving me this opportunity to present about the power of CFD and how can we utilize CFD in welding processes. So, good evening, everybody. My name is Sanjay J. So, I'm from Kaushik's International. We are located in Bangalore. So, this is about. So, yes. So, today what we are going to learn is we have a technique called as computational fluid dynamics. So, how can we use computational fluid dynamics in our welding processes, specifically laser welding processes? And how can we optimize the welding processes that we do every day, day-to-day life, or even in R&D projects? So that will be the main motive of this presentation today. So please do share me if you have any doubts and clarifications needed. I'll be very happy to resolve them through the presentation. So yes. So today's agenda is about, I'll be giving you a very brief introduction about what a CFD is, what it stands for. We'll just briefly go about laser welding, the definition, the applications and defects of laser welding. And also we will be focusing on how CFD can be used in welding processes. And also I do have some case studies from industry people and also from academia. So where they have used CFD process to simulate a laser welding process, and what have they gotten out of it? So that will be the main reason behind the case studies over here. So just briefly about my company. My company's name is Kaushik's International. We are established in the year 1996. We are located in Bangalore, Indiranagar itself. So we have a registered and works office in Bangalore itself. So for the past 2 decades, for the past more than 2 decades, we have been dealing with various products, and CFD software is being one of the main products.
So Sanjay, sorry to disturb you. That block is coming, that yellow color, the brown color block is hindering the slide. It's not showing the full slide.
Now?
Can you remove it? Yeah.
Yes.
Now this present slide, just 30% right side is not seen. You are not able to see.
Okay. I think
Sir,
we have to do unshare it and share it as something. It should not come like this.
Yes, standard sir.
Now it has been removed. It has been removed. Yeah.
Oh, okay, sir. Correct.
No. Yeah. So
now it's not there. Okay, sir. Now it's.
Yes. Once it'll just go away if I don't click on it. Sorry. Yes. So for the more than past 2 decades, we have been dealing with CFD simulation software for various applications. For metal casting applications, we have Flow 3D Cast. We have Flow 3D Weld for welding applications. We have Flow 3D Additive Manufacturing for additive manufacturing applications, and also Flow 3D Hydro for civil engineering applications, and also much more applications such as aerospace and automobile applications. Apart from this, we also deal with various productivity improvement products for metal die casting industry in India. So these are our products specifically focused on metal die casting industry, aluminum metal die casting industry in India. So we'll start with what is CFD and why is CFD needed, and how does a CFD software or a CFD technique work in overall things. So we'll go one by one here. So CFD stands for computational fluid dynamics. So the abbreviation is computational fluid dynamics. So what does a computational fluid dynamics is? So It is a technique used to understand and mainly predict how fluids such as liquids and gases flow or behave in different situations. It is basically a calculator on how to predict the flow of water, to be very superficial, or any kind of gases or any kind of liquid. How does a fluid flow with respect to time and distance, or with respect to any dynamic forces acting on it? So the applications of CFD are wide and vast. So it can be even used in very everyday simulations, everyday things, such as we have our toilet commode simulations, where we see how the water flows and how does it flow with respect to the geometry of geometry of the commode. And also we can also do simulations such as automobile sloshing, where we have an half filled fuel tank, and how does the fluid flow with respect to the vehicle moves. When the vehicle moves and hits humps and things like that, how does a fluid in the fuel tank sloshes with respect to time and effort. So there is a vast ways we can apply the techniques of CFD in our day-to-day products and life. So how does a CFD works? How does it compute? How does it predict the flow of, let's say, liquids or gases with respect to time or with respect to the geometry that we provided? So a computational fluid dynamics considers majorly three things. One is the numerical analysis part, and the second is fluid dynamics, and third one is the computer science part. So going one by one. So what happens in numerical analysis is it applies the mathematical formulas and mathematical empirical values needed for the simulation. It calculates, it uses mathematical formulas to calculate many things and applies a numerical approach to the problem. Coming to fluid mechanics is actually a branch of science which deals with the flow of flow of liquid. When there is a dynamic action applied on the liquid, how does the fluid react and things like that. And coupled with both of these things, numerical analysis and also fluid mechanics, software requires computer science. Computer science as in the physical computer itself, the processes, how does it process the problem? A problem has to be processed by the computer to get as a result out of it. So these are the majorly three things that a CFD software requires. And by combining all these things, that's how a CFD software works. So now coming about laser welding, what is laser welding? Like, unlike any conventional welding, laser welding is also a process of joining two workpieces or two metals. But here we use a high intensity laser, which acts as a heat source to melt the metal and join the two workpieces. So now there are various laser based process. One is welding, which joins the two metals. We have laser brazing, which is also a joining process, but with the help of a filler wire. We have laser cladding method. So in laser cladding, what happens is it is basically a repairing method where we use powdered metals to repair a degraded portion or a degraded surface, we can say. And also a soldering method where a no contact approach is used, where we do not touch the product, but we use liquid metal to fill the slots or the gaps. So this is about laser welding. And who uses it? Who uses laser welding processes? There are various industries that use laser welding processes, but mainly we can say, but superficially we can say about there are 4 industries that heavily rely on laser welding processes. We have automotive, where they extensively use laser welding for merging sheet metals and things like that. We have aerospace, where they use a laser cladding method to repair their turbines, gas turbines and things like that. We have electronics division, where they use laser soldering extensively for the attachments of PLC boards. And we also have medical devices such as surgicals. We do have laser stents that are actually produced with the help of laser welding processes. So the application is wide of laser welding processes. And after what is the laser welding and who uses it, it is very important to see what are the kind of defects that we see in laser welding processes, specifically in laser welding processes. So yes, so starting with, we have porosity that are one of the defects in laser welding, which are caused because of poor process parameters. It could be because of the laser speed. It could be because of poor shield gas pressure and things like that. We excuse me. This yes, we have underfilled defect. What happens is, when you have two pieces of workpiece that has to be melted, that has to be joined, because of poor limited amount of metal, it forms an underfilled issues. This doesn't completely fill up the gap that is there between the two metals. And what this causes is, this causes poor strength between the two joints, and results in cracking or deterioration in a very fast way. And we have poor penetration, where the liquid metal doesn't reach the end or depths of the gaps that are there. And because of this also will lead to poor strength of the joints and things. And we also have cracks which are caused during the solidification of the melt pool or the bead. Once the laser melts the metal, it requires some time for solidification, and the cracks can be formed because of the solidification effect, or the direction of the solidification also will be accounted in during the cracks. We also have lack of fusion. Now, lack of fusion is mainly for dissimilar metals. When we have two different kinds of metals, let's say copper and aluminum at two ends, and we melt the gap between the two pieces. Because of the lack of fusion, they find there will be huge gaps between the welding areas, and because of that, this will also lead to poor strength in the joints and lead to cracks, or lead to cracks or deteriorates very fast. And we also have burn through. Burn through is a kind of defect when the power of the laser is very high, and what is very high than what is required for the process. What basically it does is, it burns through the sheet. I'll just point out, yes. What it basically does, it burns through the sheet metals. Let's say these are two pieces of metals or sheet metals. When the laser hits at a perpendicular action, this burns through the metals and goes on. This also is a very commonly found defects in laser welding, because initially it's very difficult to find the parameters that are very ideal for this particular simulations. So all these defects can be seen, or can be seen after you do the process parameters. Once you do the laser welding process, you will find most of these defects in your joint or in your product. But the real question remains, how can we find these welding defects before we do that? It is very expensive to do an experimental setup. With the use of machine time, we have manpower time, and also with very limited knowledge of the process parameters, it is very difficult to match the ideal process parameters in the first stage itself. So it is very important for us to find an alternate method on how we can find these defects before in hand itself. So that is where a simulation software, a simulation comes in, not a simulation software. Let's understand what is a simulation. Basically, a simulation is an imitation. A simulation is an imitation of an operations or a real life situation over a system or over time. Simulation can be various types. It can be computer simulation. We can simulate in our own minds itself. I can think of a probability or a course of action that I can form. That's a simulation in my head. I can do a computer simulation. There are things like that. I can do a physical simulation also. Doing this thing, but that is the main meaning of simulation. A simulation basically an imitation of a operation, but whereas a computer simulation actually is an attempt to model the same real life situation on a computer. So let's say I am welding a joint which requires, I have a 100 mm of laser welding joint that I have to do. Instead of doing practically in a, let's say in a shop floor with the machines and the manpower required. I can do the same thing on a computer without spending the time required for setting up of the machine, putting the process parameters in, and taking the manpower. I can do the same thing in a computer simulation. Now, a computer simulation here is coupled with the techniques and the theories of a computational fluid dynamics. So that is how we get a product called as a welding simulation software. Now, a welding simulation software coupled with computational fluid dynamics is actually a specialized software or a tool that utilizes CFD techniques to simulate and analyze things such as fluid flow, heat transfer, and other related phenomena in the welding processes. So what you see on the shop floor can be simulated in the computer, but the main advantage over here is much more. One is you can go to the depth of the problem in a very deep way. So so here on the left hand side, we have a spot welding kind of a case. And in the right hand side, we can simulate the same thing in the computer. This is actually taking place, and we can simulate the same thing in a computer system with 2 blocks keeping and adding a welding, adding a laser power over it. So what this, so I'll use a welding simulation software, but what exactly does it do? What exactly does a CFD coupled with welding simulation software do for me? What can I find out of it? So it is very important for us to understand why and what does it give me. So what happens is you'll get something called as phase change. Now, phase change is something, welding is a very complex process. So what happens in welding is there'll be a solid state metal. It will be converted to a liquid state metal, and again, it will be solidified for the joining. So phase change means the same thing. We have to track how the solidification goes to liquid, how the solid body goes to liquid body, and then again, how does it come to solid body? So it is very important for us to track the phase change. Simulation software gives you the phase change. It gives you the heat transfer. It gives you the heat transfer between the melt pool being the affected areas over here. The melt pool being exactly this particular location where the metal is getting melted. So this particular region is the melt pool, and it is very important for us to track the heat transfer. We have to see how much of heat is getting dissipated to the body, or to the body of the material, or the body of the joints that we are providing. Now, this heat transfer actually will give you out the cooling rate of the product. How fast does it cool down? Because of the fast cooling rate, are you finding any cracks in the simulation? Are you finding any porosities because of the shrinkage and things like that? And we also have multiple reflections. As we all know, laser reflects, the metal reflects light. And when when a high intensity laser or electron beam hits the body of, let's say metal, let's say aluminum or any kind of steel, there's a tendency of the material to reflect the light. So because of the reflection of the light, there's a heat, because of the reflection of the light, there's a refractions that are taking place. And because of that, there's material melting. And also you will have a heat loss because of the reflections. So that also has to be accounted for. And we have to apply shield gas pressure, because to avoid oxidation, it is very important for us to apply shield gas pressure. So what we can see is the shield gas pressure that what I'm providing for the process, is it correct? Is it needed, or should I increase the shield gas pressure? Should I decrease the shield gas pressure, and things like that? And surface tension of the liquid metal, when the metal is in molten state, it is very important for us to track the surface tension of the metal, because the surface tension will finally lead to the porosities in the joints and things like that. And also to provide the laser movement. Let's say your laser moves at there's a specified way how a laser moves in the shop floor. So it is very important for us to give that laser movement to this. And by giving that, it shows us, is the laser speed sufficient for this? Is the laser speed, let's say I give 3 meters per second for this particular product. Is that 3 meters per second sufficient? Is it too much? Is the time too much? Can I reduce the time? Let's say within I can reduce the time by increasing more. Can I increase the velocity more and decrease the final time? So there are things like that what you can play around in some cases. And also solidification has to be considered with respect to the cooling rate and also heat transfer coefficients. So once your metal starts to leave out heat, once it is in liquid state, it starts to leave the heat out. It could leave the heat to also the atmospheric air or atmospheric temperature. It can leave shield gas can also act as heat extractors, and also the metal will extract some kind of heat from the melt pool. And all these coupled with, you'll get a solidification. How does it solidify? From which direction does it solidify? It is very important to know, because solidification also can cause an effect such as porosities and shrinkages. And also it is very important to track the viscosity of the liquid metal in the simulation. What happens is, because of the viscosity is a temperature dependent item. So the higher the temperature, the viscosity, the resistance of the flow material reduces. So with respect to this, your melt pool dynamics changes. You can find splattering in your welding processes. So those kinds of things has to be considered in your running. Those are the kinds of things that you will get out of the simulations once you are. And these are very limited. These are very superficially mentioned over here. But what you can take out of from the simulation are many in number. So it is just about our interpretation about the simulation and how we take it. Now, why is there a need to use the CFD software? Why do we need to model specifically a laser welding processes when before you take the trials in the shop floor? One is, there's a lot of cost savings. So by using a CFD technique or a CFD software, what happens is the need for expensive prototypes and testing is avoided. You don't need to initiate. It's very difficult to achieve the ideal process parameters in the first stage itself. So how many experiments will you take on the shop floor? 10, 12, 20? The more the number of experiments you try to take it on the shop floor, the cost increases by that. So instead of that, you can use a simulation software where you can do multiple experiments to idealize a process parameter, and that can be later incorporated. Once you're convinced, that can be later incorporated to the machine and to the shop floor and get the designs approved. And also design optimization. Now it's not only about finding out defects in the welding joints. It is how can we make the process better. One is defect prediction, but we should also focus on increasing the yield. So it is very important. So questions such as, do we need to use such laser power? Can I decrease the laser power? Can I increase the speed so that I can reduce the time of the process? Do I need such kind of filler material? In things like that. Those are the kind of questions that can be answered by a CFD software. So that is our design optimization. And complex flow analysis. What happens is, a welding is a very fast process, especially laser welding. It's probably seconds and milliseconds of time. So it is once you complete the laser welding process, you can take out the component and see what are the kinds of defects you have. You'll have porosities, or you'll have sometimes burn through at some locations. You'll have some materials might have not penetrated in some locations. But why are these forming? Why is a very important question. So why this is forming is mainly because of the melt pool dynamics that are taking place. Mainly because of the melt pool dynamics that are taking place. So it is very difficult in the shop floor to track this melt pool dynamics as it goes on, because the melt pool takes place in a micro level scale. It's very difficult, or I would say even impossible, to track how the melt pool is acting on the shop floor. But a CFD software helps you and to do that in the simulation, in the computer itself, and you can see at micro level what is happening. how is the splatter happening? How is your melt pool dynamics forming and things like that. So it enables and gives you insights to intricate fluid phenomena and with respect to viscosity or surface tension of the fluid. And also about innovation and exploration. The kind of simulations that you can do on a CFD is the sky's the limit. You can try any kind of process parameters you want, and even process parameters that are impossible to do on a shop. What this actually helps you is, this helps you with testing unconventional ideas, new ideas where nobody has tried it out. And it also helps you to push the boundaries of traditional engineering approaches that we have today. And also there is also a time efficiency that can be achieved. What happens is CFD enables us with quick evaluation. We can easily run a simulation and see what kind of defects or how can we increase the yield of this particular product, and enables quick evaluation and optimizing of defects. So this reduces the development and cycles time and time to market for the product. So these are the advantages of using a CFD software for laser welding applications. So here we have a basic comparison. This is why you should use CFD software. So if you see, these are two different simulations. This is one simulation and this is one simulation. On the left hand side, this is both are spot welding simulations, and you have two plates or two blocks. We have laser penetrating. The laser has been hidden intentionally. So there's a laser penetrating, and we are trying to see how efficient is the joint. So if you see the first one, because of the laser power indication, there is a huge void that is getting formed. Void means porosity or huge porosity or a bubble that is getting found over here. But whereas if you see the second iteration that we have done, there's a very good, very clear joint over here, and there is no porosity over here. Compared to this, we have a very small porosity, but we have got. So these are the questions that you get answered. Is my process parameters correct? Is the laser power what is needed? Is it sufficient? Is it very high? Is it over what I require? How can I optimize it? So these are the kind of questions that a CFD software helps you to. We also have a laser welding of a T joint. So we can try different iterations. We can change the process parameters in the way we see fit, and we can try to increase the efficiency of the simulation and also the parameters. So on the left hand side, you can see the beam dia, the laser beam dia is about 300 micron. On the right hand side, you can see the laser beam diameter is about 400 microns. So what this basically does is, you can see on the left hand side, it is not the melt pool dynamics or the bead that is getting formed is not very good compared to what I'm getting out of 400. But sometimes it might not be the case. Sometimes a 300 micron will give you better results than a 400 micron. But in this particular case, the 400 microns gives you a better result than a 300 micron beam diameter. So these are the kind of questions any engineers will have. Should I use 300? Should I use 400? Should I use 500 microns? How do we answer this? How do we validate it? We have to validate it. I cannot just guess I can use a 400 microns in the parameters. I can just add 500 microns in the machine. It is very important for us to validate us on in a scientific way, in a science way. So it is very important. So these are the kinds of things that you can change the values and work on or play on in the simulations. And also things like pulse and continuous laser welding. What we have a pulsed laser on top of it, on the top window. We have a continuous laser on the bottom window. In pulse laser, it is turned on and off in discrete time with repeatable intervals. We have a frequency for that. And in continuous, the duration of the laser it's constant, and with respect to the body, it moves over. We provide the direction of moving, let's say X or Y axis, and the laser moves up. But there are specific advantages of pulse and also continuous laser. If you look at pulsed laser, we can control the heat affected zones. And this can be very helpful in electronic manufacturing, where the heat affected zones should be constrained, and they don't have the, they cannot afford the heat to lose out in any way possible. But when it comes to continuous laser also, we cannot do a very deep penetration of metals in pulsed welding. But whereas in continuous, you can do a very deep penetration and also dissimilar metals, where you can melt two different kinds of metals and join two different kinds of metals using a continuous laser welding. So in this image, what we are trying to see over here in this video, what we are trying to look over, or what we are trying to interpret as, one is the melt pool. So you can see these are the affected zones, and this is the liquid metal that is acting. How does the liquid metal flow with respect to the laser beam hitting on it? You can see the here how much of the, exactly how much is the melt pool, or my bead, or my weld bead as you call it. How much is my weld bead and things like that. And also it is showing the temperature of the metal or the liquid metal at this particular location. It's around 2000 degrees Kelvin. And then there are heat losses. As I mentioned, the body consumes a lot of heat from the melt pool. So how does the heat transfer takes place? How does the solidification from back? In the front, it is actually in liquid in stage, because there is a because the laser metal is laser is acting on it. But from the back, we can see it is solidifying. It is slowly solidifying, and it is losing out the temperature. So the solidification front is from the back to the front. So, and also it's a known. What is very trending is about laser shaping, and also about keyhole and conduction. So keyhole stands for deep penetration. Keyhole is for when you want to penetrate metal deeper. So things like that. So that is a keyhole kind of laser welding. We have a conduction mode. Conduction mode is much more like thick beam, and it doesn't penetrate deep, but it focuses only on the very small depth. And whereas in keyhole, the area of the region is very small, but the depth is very high. Whereas in conduction mode, the area is quite large, but the depth is very small. So there are these two kinds of welding, keyhole kind of welding, and also conduction mode kind of welding. They both have their advantages and disadvantages with respect to one another. And also beam shaping, let it be keyhole and conduction, they can greatly impact the melt pool stability. Melt pool in the sense the bead that you're getting formed. So how does your bead getting formed? And once my welding is done, once my joint is formed, should I post process it? Should I have another processing technique to make it a much more better joint? So those are the kind of questions you should ask before you're joining a metals, and those are the kind of questions you'll be answered by the CFD software. And also new things such as multi-core beams. And we can see these are actually multi-core. Basically, they're called as donut shaped. So where they'll have 2 or 3 rings of laser power hitting on the model. So what happens is, by using different shapes, such as multi-core beams, and also there are star-shaped beams that are coming out now. By using these kinds of beams, you can stabilize your melt. When you stabilize your melt pool, what you're trying to achieve by stabilizing your melt pool is you're trying to reduce the amount of post-processing required after the welding is done. Should I file later? I'm just saying you can reduce some kind of post-processing once you stabilize the melt. If there are a lot of dynamics that are taking place in the welding, let's say the melt pool is acting in a very dynamic way, a lot of what happens is there will be a lot of splatters that get formed. There'll be a lot of porosities that get formed. So it is very important for us to maintain this melt pool stability for a very rigid joint. And also this leads to faster production and, as I mentioned, lesser post-processing of the joint itself. Now, coming to about welding dissimilar metals, there are specific applications where they use dissimilar metals. Not dissimilar metals cannot be used everywhere. the applications include electronic and battery manufacturing. We have automotive purposes and also aerospace applications. Now, the main benefits of using two dissimilar metals is one is save on material costs. Let's say I don't need one particular material over the complete model. I can substitute that for a cost cutting kind of a thing, and we can do things like that. And also product can be optimized by using a welding of dissimilar metals. But there are challenges when you're trying to weld dissimilar metals. One major important thing is not all the materials can be successfully bonded. Here in this particular example, we are looking at copper and aluminum. And what we are trying to see at only one particular location, what is happening and what is the porosity that that we are getting. And also we have to consider what kind of materials to go with. You cannot add iron or aluminum together. There are certain parameters that have to be met before you use a welding, before you weld dissimilar metals. And also what we need to consider is solubility between the metals. Thermal expansion, very important when it comes to two different metals. Melting rates, also quite important, because you cannot have a material that melts at 400 degrees Celsius, and you cannot have another materials which melts at say 1500 degrees Celsius. So it is very important for us to note all these points. And also intermetallic compounds, the composition and also corrosion properties of these materials should be considered in melting. So while welding dissimilar metals, what do you get out of it? So as I mentioned, it is very important for us to know what we want before we do the simulation. What do we need from the simulation? What kind of results do I want out of it? So here you can see we have two dissimilar metals such as aluminum and copper. So what we are trying to see is one is temperature gradient. Temperature gradients is basically how the temperature is transforming with respect to the laser. So here initially it was at a liquid state, but as the beam moves on front, this solidifies and leaves the temperature down. So that is one. That is what temperature gradients is. We should also consider the cooling rates. Once the laser moves on and one particular location is in liquid state, how does it cool? With what rate does it cool? From where is it leaving the heat, excess heat? Is it leaving through the body of the metal itself? Or is the shield gas playing a very important role in cooling the melt pool and things like that? And also cross-sectional profiles. This is one of the main advantages of CFD. You can add 2D planes. You can see this. These are actually 2D planes, and we can see how they are actually formed and how metal 1 and metal 2. We are only trying to see how the metal 1 and metal 2 are fused together. And we can see the surface finish of the melt pool, means surface finish of the joint. We can see the melt pool stability, because the melt pool dynamics changes with respect to many things. But when you're melting two dissimilar metals, there'll be a change from how it acts in a similar metals. Let's say in aluminum, it'll be different. In copper, it'll be different. But when you combine, it'll give me another different kind of a stability. And also main important thing is the fusion of the two metals. How well is it fused? How efficiently is it fused? And how strong is my joint? And also, of course, the porosity or any kinds of defects that are found. Now, actually moving on to the case studies of the product of the CFD. So most of the case studies are, all of the case studies, sorry, are shared to us by our customers who are using CFD process, for their welding applications. Excuse me. Okay. Okay. So yes, all of the case studies are given to us by by the users in commercial lane, such as industries who have R&D centers and things like that, for research purposes and things like that. So the first case study is from Shiloh Industries. So this is a very a simple simulation that they have done, and this can be used in our day-to-day processes. And how do Shiloh Industries use CFD is what we can get out of this particular case studies. So we have two parameters. So you have sheet. These are actually two different kind of sheet metals. We can say we have two plates over here, which is 1.8 mm and this is 0.7 mm. And this is case one, and we have case two, where this is actually at a distance. So this is actually perfectly matched in the bottom area, but here we have wedged it at a height to do the simulation, and the thickness of the plate is also different from the first one. But if you make a note of it, the power is for the both simulations are the same, which is 3,300 watts, and the speed is also same, which is 4.5 meters per minute. Only the plate thickness is changed with, and also the plate's position is changed. So they are trying to see what kind of defects will we get and how efficient will be the joint be. So those are the kinds of things. So this is the first setup, as I mentioned. So we have two plates, which is 1.8 mm and 0.7 mm. We have a laser. The red rectangular or cylinder indicates the position of the laser and also the direction of the laser, which is directly perpendicular to the plate over here. So, and the direction of the laser is towards the right side, or in x-axis, as we can call it. So you can see this particular video or window. This is the top section, and this is actually the side section. And what we are trying to see here is only the solidification front. The blue represents liquid state. The metal is in liquid state, and the red represents the solidification front. So what we are trying to get out of it is, one is how fast is my cooling going on, and what from which direction is my cooling going on. If you see here, always solidification front or the solidification starts from back side, because the laser front is going in the front, and there are no heat sources that are providing constant heat at the back of the simulation. So it is the metal itself is absorbing a lot of heat and leaving to atmosphere, or there could be also shield gas pressure will carry a lot of heat as it travels because it has some kind of pressure and velocity. And you can see the agreement between this is actually the actual process, the actual cross section what they have provided, and you can see the simulation results from the CFD software, and the profile agrees with that very much. So the agreement between the experimental and the simulation or numerical analysis is quite good, is what they say. And coming to the second study, I mean the second different process that they had taken was the plate thickness was 1 mm, but keeping the laser dia and also the laser power constant and also the laser speed constant. This arrangement of the plates is quite different from the first one, and they applied the same laser power to it, and they see what kind of defects or how is the solidification taking place here. Here you can see one kind of defect, that is burn through. So what basically is happening is the welding is completely deeply penetrating. It is deeply penetrating through the weld and it is moving forward. But even though there is a burn through and it is deeply penetrated, the liquid metal comes back to the center and forms the joint and moves forward. So this is kind of the defects. Even though there was a defect in the process itself, the melt pool corrects itself and gives us a very rigid joint. And you can see the cross section over here. In the previous case, if you had observed, only the top section had a profile. The bottom section did not have a profile. But in this particular case, because of the burn through, we are getting a profile on the top section and also on the bottom section, which can be seen in the software also, which can be seen in the results of the simulation software also. So, so you can see the process over here. And this is the end of this particular case study. And Yes, and this is one of the most interesting case studies we can see over here. This is actually how do we track? Why is a porosity forming in a weld, and how do we track it? Is something that we are trying to see over here. Um, so this is actually a study from General Motors and Shanghai University in China. So the main process, the main thing what they're trying to see is the welding speed. How does welding speed and angle of inclination affect my process parameters? So that's what they're trying to see. So majorly there are two kinds of defects. One is metallurgically forming porosities, and the second one is keyhole formed porosities. When there is keyhole formed porosities, they are actually non-linear. They don't have particular shape or size. But metallurgically formed induced porosities, they have a particular shape, let's say circular or sphere in shape. Any kind of porosity, they eventually lead in cracking. So these are the kinds of physics, or these are the kinds of things that they're tracking in the simulation: phase change, laser heat input, melter dynamics, vapor dynamics of the metal, liquid metal, and things like that. So here we have a bunch of images from the simulation results and how a porosity is getting formed. So when the laser hits, we have a laser hitting over here. It is not visible in the image. So when the laser hits in a very perpendicular direction, what is happening is there's a recoil pressure or a vortex. The melt pool here forms a vortex, which makes the melt pool or the liquid metal to rotate in this particular vortex. The vortex rotates like a whirlpool. Now, because of this, when and unstable, and when after a certain time, there are unstable keyholes. Because of the keyholing, because of the depth of the penetration, there are unstable keyholes, and this particular front falls on the front and forms these bubbles. It's like a wave coming over and um, in a beach, and it falls on the sand. So these are the kinds of waves that comes over and hits, and because of that, there are bubbles formed, basically voids that are formed. So that is majorly because of the melt. So most of the bubbles, or some of the bubbles tend to move up and go out of the melt pool, leaving with clear melt pool or clear bead. But sometimes what happens is, as the bubble that are formed enters this vortex, it's a very, actually this is a very high power vortex, and this circulates at a very high velocity. And because of that, some of them not end up getting out of the melt pool. And because of the solidification front that is coming from the back, they actually catch this porosity and cools the metal down, which makes the porosity to not go out of the melt pool. The porosity will only go out of the melt pool once it is still in liquid condition. Once it solidifies, it holds the porosity, forming a void. So we can see an example of the porosities that are forming in with respect to video. So this is, we are seeing the solid fraction. Blue indicates solid and red indicates the liquid metal. And here we are trying to see the depth of penetration. What is that? And also there are extra physics that needed to be accounted for. So we have something called as upwards vapor pressure, which has to be accounted from, which the vapor pressure forms from the bottom of the melt. So that tends to come up and go out of the melt pool, but sometimes they're trapped in the melt pool itself and form porosities. And HTC in the keyhole should be accounted for. When the metal is hitting, how is that my heat transfer going out of the simulation? That should be accounted for. And we have multiple laser reflections, because when you have laser reflections, your laser power decreases over time. So that has to be also be accounted for. Now, there are very different methods that you can get hold of this laser reflections. One is Fresnel equations, a physical form, and we have temperature dependent and also cost functions with respect to the angle of the laser. So we can see the porosity formation in 3D. On the left hand side, we are trying to see how the surface metal affects my melt pool, how my surface metal is getting affected by the melt pool, how much is it getting mixed with this one. And on right hand side, we are trying to see the temperature of the melt pool. So you can see the temperature of the melt pool here is very high, and from the back side, it is getting cold, and that helps to capture these voids and forms porosities. And also what they came to the conclusion was, once they can increase, if they can increase the speed of the laser, of the movement of the laser, they can decrease the porosities that are formed. You can see the examples over here. With 6 kilowatts and 12 meters per second, this is a very high speed laser. There is no porosity, there are very minimal porosities formed. But with 2.5 kilowatt and 3 meters per second, you can have a lot of porosity. The difference in kilowatts is because they wanted to maintain the depth of the melt, depth of the penetration constant. So that's why we can see a difference here. Now, actually, this is a very interesting graph which says with respect to the welding speed, and also when you increase the welding speed and also the power, the vortex that are formed, as I mentioned, the vortex or the whirlpool that are getting formed over here, the effect of vortex is very less, as you can see, in a very high welding speed and high power, because the area of the melt pool increases. The vortex has a lot of space to turn, and which reduces the magnitude of the vortex. Whereas in very small, when the laser is perpendicular in direction, the vortex has a very high intensity, and this traps the bubbles or the voids that are getting formed. Here, the laser irradiation is actually on the front of the metal pool or the front of the metal. But here, the laser irradiation, you can see it is over exactly below the laser effect. So these are the main reasons why you can get porosity. And you can also see an example of an image of low speed, low kilowatt power, how porosity you are getting. Same thing, high speed, same material, same parameters, with just increase in speed and also increase in power, you can find a very good a clear metal, and also you can find a very good solidification rate with respect. So, but when we focus on high speed laser welding, there are problems that arises, whereas narrow joints with width leading to poor tolerance for gap conditions. And also at the end, when the laser is getting turned off, you will find a huge crater that are getting formed. So that is not actually wanted in any kind of process parameters. So, but laser welding have these effects. And also high velocities can result in insufficient penetrations if you don't provide the exact power that is needed. And also there is a limitation of how much high power you can go with respect to machineries and things. But instead of instead of high speed welding, we can also use laser lap welding with oscillation. In oscillation, what there's a flexibility where you can actually minimize the porosity, and also control a lot and manipulate a lot of process parameters in oscillation type of welding. So this is one advantage over fast laser welding. And also there are benefits of laser welding with oscillation. What improved first time quality through oscillations, we can actually enable high speed welding with avoiding keyhole induced porosities, as I mentioned. Alternates between keyhole and conduction because it turns on and off. It enables adjustment of critical weld and again, that's the weld beam dimensions. We can manipulate those dimensions, and also the strength of the joint, and improves the gap bridge between the sheets. And in case of oscillation, you can also have zigzag kind of motion, or this is a zigzag kind of a motion, but whereas this is actually a circular kind of a motion, where this spirals around the joint and moves forward. So coming to other laser-based processes. So we have a laser soldering, where it is a non-contact way of melting a metal and adding it to particular gaps. So these are actually diode laser is used to melt and solder the wire. So the advantages are mainly minimal heat affected zones, and also it is very highly precise. Minimal heat affected zones, these are also very well needed in electronic manufacturing. So here in this simulation, you can see we have a laser which is hitting, and as the filler wire moves towards the laser, it melts it and joins the particular gap over here. So this is actually a point of laser welding, what we're trying to see. And coming to the next process, we have laser brazing. It is actually a joining of two different metals, but with the help of a filler wire. But there are advantages of laser brazing also. High mechanical stability, minimal heat affected zones, and also smooth surfaces can be. Here I have a very small case study on laser brazing process. This is actually given to us by Research Center for Advanced Manufacturing, Southern Methodist University. Here, what they're trying to do is to determine the influence of brazing parameters such as heat source, process parameters, and materials on melt pool stability. There are actually two sheets, steel panels of galvanized steel panels, and the filler wire is copper. And the simulations provided. So here you can see this window where it indicates the video of the process, where there is a laser hitting. This is a filler wire, and this bridges the gap between these two sheets. If you see the first window, here in this particular window, we are only focusing on the melt region. How much is my melt region? If you see only this much is your melt region, because your laser is hitting only on the filler wire, and it is not much affecting your steel plates. Here, what we are trying to see is how much is of the particular simulation is of steel. If you see, this are steel plates, so these are visible in very bright red, and these are actually copper wire, so it is in blue color. So these are the kinds of things that, because of there is two different materials, it's very important for us to distinguish after the melt pool. Is there any fusion? Is there any excess fusion of materials that are taking place into account? Things like that. And you can see the experimental and validated results. We can see it's actually cut at the 2D cross section, and we are trying to measure the length of the bead. This is actually a 0.4, and simulation we have got it at 0.77. So you can see the agreement between the simulation and the experimental is quite good. And coming to next type of process, we have something called as a laser cladding process. Basically, laser cladding is actually a repairing process where we add powders or filler wire to a particular location to fill up that gap. It is not a process of joining, but it is majorly a process of repairing a certain process. It can be either filler wire kind, or it can be either with respect to powders kind of kind. So coming to laser based metal deposition, there are numerous advantages of it. So suitable to create functionally graded materials with complex geometries. Different powders can be pre-mixed. Different types of materials can be pre-mixed to create a custom alloy. We can control the accuracy. We can manipulate a lot of process parameters here with respect to feed rate also, and control the accuracy of the product. And the simulations help to process it. How does CFD help in this particular cases? We can optimize the process parameters such as in powder injection rate, the movement of the bed or body or things like that, and also laser parameters. This is actually my last case study. This is actually a laser cladding process done by Mitsubishi Heavy Industries. The main purpose of this heavy industries is actually they are working on gas turbines. So where the gas turbines is made up of single nickel crystal blades, which are used in gas turbines, they're very expensive, and they cannot be actually replaced to very different interval, or when they have a very small damages that are taking place. But it is very important to repair them and then put it to action. So laser metal deposition, or LMD as we call it, or cladding, can be used here. However, the weld metal or the material or the metal powder that is going into the turbine blades need to have the same properties or same crystal orientation as the base metal. So the materials needs to be taken care of. Both the metals needs to have same kind of chemical composition. The objective is to actually maximize the growth of single crystal in the weld metal. So to see how does the bead or your one powder drop, how does it affect your complete turbine blade is what we are trying to see. So how did they achieve it? They calibrated numerical parameters with the experiment, and they actually also they controlled the thermal gradient and the solidification rate at which depend on the process parameters used. So here you can see a cross-section view. This is actually a single crystal. This is a one particular crystal. We are looking at a micro level here. This is a base metal and this is a single crystal. When the single crystal hits the plate, which with also the power of the laser which melts the blade, and we are trying to see what kind of bead is formed over there. You can see here. So they had a set of values. They did not have the final values. They had a set of values and they had a range. So if you see, the scanning speed was 30 to 105 mm per minute. The laser power was 100, somewhere between 100 to 1000 watts. And if you see the powder feed rate, they had a value of 1.2 grams per minute to 2 grams per minute. But by keeping all of this, they did numerous number of simulations. They did numerous number of simulations, multiple simulations. And you can see some of them are provided. We have here laser power of 250, 300 watts, 400 watts, and 500 watts. What is happening here is, this is of the numerical analysis from the software. And this is actually an experimental result. This is one bead, one particular powder. When at 200 watts, when it hits, we can see it doesn't completely go and form a layer on the gas turbine, but it just sticks to it and holds it there. But on 300, we can see a bit of development, but it still needs to penetrate. And if you see, when you try to increase the power of the laser, let's say 400, 500 and things like that, you can see the crystal forming at a very good rate or as we require it. Now, by keeping these things and when they have done multiple simulations, they actually formed a graph. So we can see this particular graph. So on the left-hand side, it shows laser power. So here we have laser power, and bottom we have scanning speed. And here we have the length of the bead or the length of the crystal that is getting formed. So the maximum is 0.8 mm and the minimum is 0 mm. So with the help of these graphs and all the values from the numerical analysis and CFD, they made this graph and they have found a sweet spot. Now this particular region is what we call it as a sweet spot. Excuse me. Now what this achieved for them, they formed the perfect crystal formation on the crystal blades with minimum of what is required. They did not go for maximum of what is required. They could have even go now. What they've achieved is 650 watts of power, scanning speed of 60 mm per minute, and also powder supply rate of 2 grams per minute. This can also be achieved with 1000 watts of power. But it is very important for us to keep in mind the yield and also how can we distribute the heat also. So it is very important to, so they have found these ideal conditions, ideal process values with multiple simulations and interpreting those simulation results for their process parameters. So this is my last case studies on laser cladding processes. So that solves my presentation today. So thank you very much for all the attendees that are here. And sorry, I believe if there are any questions, please you can unmute yourself.
Thank you, Mr. Sanjay. Really, it was an interesting talk by you. Really, we enjoyed your talk. Really, how the CFD can be employed in laser welding process particularly. So I have a question. This you restricted your talk to only laser welding, but this is applicable to all the welding processes, isn't it?
Sir, actually, the way we simulate laser welding, there are certain parameters that are required. We need something like laser power. We need the heat source of a laser can be easily simulated. Okay. But when it comes to other kinds of conventional welding methods, it's very difficult. There are ways we can simulate them, but that requires a specialized process that we are looking into it. It is possible, but I'm just saying it's very difficult to manipulate them into our values. So that's why.
The CFD technique long back, a decade back, we employed in our boiler, flow, duct flow, air flow and all. We conducted about 2 days seminar at NIT Trichy with the collaboration of BHL. Still, it was a successful seminar, and people participated from throughout India. In foreign delegates also came. It was successful about CFD that I remember some time back.
Yes, That is pressurized gas or pressurized, you will have boilers,
Yeah,
you will have pressurized boiled
Ah.
water or some kind of gases. So we are trying to see pressurized gas over there. Let's say liquid vapor, water vapor, pressurized water you're trying to see over there. What we are trying to see here is liquid metal. The physics of the CFD are same. What we are trying to add applications to it. There are multiple applications we can add. We can see additive manufacturing, we can see metal casting, we can see aerodynamic simulations, aerospace simulations, automobile. So it depending upon the applications we can see, we can manipulate it. The CFD software is what we are trying.
Now the participants can, sir, you can, Sanjay sir, you can answer your screen so that people will come gallery, they'll ask questions, you know. You can unshare your screen. Yeah. Who are all your customers? So you have served this, simulation technique. Any of our major customers in India, abroad, and all for you, for your company?
As I indicated from the case studies itself, we have Shilo Industries, we have Mitsubishi Heavy Engineering. In India, we have supplied it to NIT Tiruchi also. NIT Tiruchi uses Flow 3D Weld actually. Our particular product.
NIT Tiruchi, which department, sir? A mechanical department?
Not mechanical. I believe it's a production engineering department.
Maybe who is the professor there? Coordinated?
I am
maybe Dr. Dorai
Paneerselvam. Yes.
Paneerselvam. Okay.
Dorai Selvam.
Okay. Right.
Not mechanical. I believe it's production engineering department.
Maybe who is the professor there? Coordinated?
I am So if there are any questions in chat box also, we can check it.
Sir, I am Ilango here. Sir, I am Ilango here.
Sure. Yes, sir. Hello.
Ilango here. Sir,
Yes, sir.
how the heat input and sealed gas is estimated and controlled by the computer?
Yes, actually, sir, as I mentioned, CFD is a combination of different things. One is numerical methods, that is basically mathematical solvings. Second is physics, fluid mechanics. So there are a lot of physics from the fluid mechanics that are taken into account. When the laser hits, the laser has a certain power, let's say 100 watts of laser. It hits a body of a metal, let's say aluminum or any kind of metal. Now the heat transfer is what I've mentioned is tracked by the CFD software. The CFD software tracks it. And also the CFD software will also have the database at what temperature does the metal melt. Let's say aluminum. Let's say the liquid temperature of aluminum, let's say it's about 600 degrees Celsius. It starts to melt at 600 degrees Celsius. When the laser power hits, let's say 100 watts of laser power hits, there's a heat transfer that is taking place. And when the metal reaches above 500 or 550, it slowly starts to become liquid metal. It slowly transforms it. It tracks those heat transfer conditions for every second or every microsecond. It tracks those heat transfer conditions. That is how it tracks it. And on this, we are applying a shield gas. Let's say I have a nozzle which is supplying a shield gas. So that is also getting tracked. That shield gas is coming, hitting the melt pool. We are tracking that boundary. There will be a boundary between the shield gas and the liquid metal. So the computer knows this is the shield gas, this is the molten metal. And as the laser moves forward, and there will be dynamics. Let's say it is circulating, the melt pool is moving there, here, splattering, and things like is happening. It tracks it. So those are the kinds of things. It's a combination, as I mentioned, as it's a combination, it helps to track all those things. So to mainly answer your question, mainly it is basically a heat transfer. One is when if you ask how does it melt, it is basically mainly because of the heat transfer that is taking place in the simulation.
Okay, sir. Then what is the maximum thickness of the metal to be joined by laser welding? Maximum thickness.
Maximum thickness, no, actually what happens is, if you're looking at spot welding, as I mentioned, we have two kinds of things. One is a keyhole kind of welding. One is conduction kind of welding. Now conduction, when you use conduction kind of welding, let's say you have a butt joint and it travels on the top, but it is very difficult to just give you a value on the maximum depth of the this one. It depends upon the laser power. Specifically speaking, it depends upon the laser power and also the how fast is the laser moving. Because if it is too fast, the metal doesn't get enough time to absorb the heat, and it doesn't melt, and it just heats the metal and just moves forward. So to give you a specific value, it's very difficult. What is the maximum length I can depth or I can weld the joint? But the parameters actually affect these kinds of things. So,
Then what is the
Mr.
defect controlling system in computer?
yes,
Defect
actually,
controlling system.
yes. So there are a lot of values that you give for the simulation. Let's say you give them simulation speed. I mean the welding speed or the shield gas pressure, other things like that. So let's say I found a porosity at this particular location. Let's say at a distance of 1 mm or 2 mm from the base. So first thing is why it is getting formed. Is it getting formed because of the laser? One is laser. Should I increase or decrease the laser power? So there are a lot of parameters that affect. Let's say in butt joint itself, we have laser speed, we have the chemical composition of the metal and things like that. So a lot of parameters are there. We cannot just say for one parameters. But if you ask me, mainly it is because of the laser power. It is because of the power of the laser. It could be sometimes high, it could be sometimes low, and because of that porosity form. And also there is actually the effect of shield gas also should be considered here for the porosity formation defects. And other kinds of defect also, if you have underfilling issues, if you have not enough penetration in the joint, that is also because of less heat or more heat. If it is more heat, you will burn through the weld joint. If it is less heat, you will find underfilling issues. Less fusion, not much. If there is no fusion between the metals, that is also because of laser power, or it could be because of the laser speed. Mainly, it could be because of the laser parameters. So we can manipulate these parameters in the software, and we can find out what are the ideal conditions for the simulation.
So Sanjay, you
Okay.
have a lot of appreciation in the chat box. Just I'll read out the names. That is one Mr. Manavalan, the safety expert from BHL, and Mr. Praveen Selvam, informative session. The Guldeep Singh Chauhan, nice presentation. Dr. Krishna Mohan, nice presentation. Nageswara Rao, to everyone, wonderful presentation, sir. Thank you. Nice presentation. Then Dr. Parag Gale, he is also a nice presentation. And Dr. Vellala Garango, he has also he has mentioned as a wonderful presentation. And our Karupasamy, Dr. Karupasamy, past chairman, has appreciated your efforts, sir. And there is one more question, sir, the chat box. Can I use this? One Mr. Nageswara asked, can I use this software for other processes like arc welding or TIG or MIG weld? Please answer, sir.
Yes, as I mentioned, the reason for choosing laser welding is it is possible to simulate those things. It is possible to simulate TIG welding or arc welding, but the power of instead of power of laser, we'll have to introduce some other way to melt the metal, because you can see in laser what we have developed in the software is there is a tool to add the laser power. So which in turn is absorbed by the metal and melts the particular area or section. But when it comes to TIG and or arc welding, the laser power is quite less there. It's a combination of other things. So we can simulate it, but not to an extent of other ideal conditions. It's not to an extent of complete 100% accuracy. We can simulate it in let's say about 60 or 70% of the simulation by melting it and seeing the solidification rate or things like that. But to see as much details of laser welding is I am not aware of those things, because as I mentioned, there's a tool in the software to provide a laser power to it. But when it comes to other applications apart from laser welding, it is very difficult to provide that particular heat source there. So that happens. But instead of giving heat source, you can also provide other things such as you can already melt the joint and you can see the solidification rate, which might lead to crackings, or you can see find out the cooling rates of the particular joint or things like that can be done. Yes.
There is one more appreciation for you, Madam Uma Mageshwari. Uma Mageshwari has appreciated your presentation.
Thank you. Thank you. Thank you very much.
Participants, if you have any questions, you can ask to the today's guest, chief guest. Otherwise, we will move on to the next agenda. And one more, Mr. Rajeswara Rao Mandava, he is also appreciated your very nice presentation like that. Yeah. Yes. Now appreciation. Really, it was a very good show, Mr. Sanjay. Really, we enjoyed your presentation. Thank you so much. You brought safety, in laser welding, A to Z, everything, and we understood many things today. Thank you so much for sparing your valuable time with us. Really, we enjoyed your lecture. Thank you so much. With a lot of more than 50 PowerPoints, PT. Very good quality PPTs. Really, we enjoyed. So, thank you so much.
Thank you.
Now,
Thank you
participants, yes, sir. Yes, sir. Please tell, sir.
No. Thank you very much for your time also, and I thank the participants for
attending. Thank you. It was a very good presentation. We enjoyed. Thank you so much. Thank you.
Thank
you. Participants, if you have no other questions, we will move to the next agenda. Just wait a few minutes, sir. Some more agendas are there. Now I call upon Dr. Kevin R. Kumar, our Honorary Secretary, to announce the next week's program. Over to Dr. Kevin R. Kumar.
Good evening, sir. Thank you. And our next week lecture program will be on Tuesday, coming week Tuesday, and the topic is Design Thinking for Innovation, and the speaker is Dr. Murali Bhaskar from Rajalakshmi Engineering College, Chennai. And I request everyone to participate in this program and also to invite your friends and colleagues for this program. It's completely free, and e-certificates will be issued to all the participants. Thank you.
Thank you, Dr. Kevin, for announcing next week's program. Now, I thank all the participants throughout India who has participated. In other countries also people participate. Thank you so much. And thank you all the dignitaries who participate. I call upon Engineer Suresh Kumar, Honorary Secretary from Indian Trichinopalli branch, to propose vote of thanks. Over to Engineer Suresh Kumar.
Good evening to all of you, sir. I would like to express my gratitude to the organizers of the IEI Trichinopalli Local Center for the opportunity to me to deliver the vote of thanks. Our first and foremost thanksgiving goes to the Almighty God, the creator of you and me, for what we have and what we don't have. Mr. R. Silvaraj, Chairman of Indian Institute of Welding Trichinopalli branch and past chairman of IEI Trichy Local Center, coordinating and organizing this webinar. He is a man blended with the industrial experience and a good academic profile. He is regularly organizing the events. And today he is delivered the welcome address. I record our sincere gratitude to you, sir. Mr. Lakshmanan, today he is given the introduction of speaker. I record our sincere gratitude to you, sir. Mr. Sanjay, engineer from Kaushik International, Bangalore. He is the person speaks constructive words and do many wonders. I express our sincere thanks to you, sir, for your presentation, for your stewardship, support, vision, and commitment. I thank to Mr. Kevin R. Kumar for announcing the next week program. And foremost all, I thanks to all the participants, those who are regularly participating in the events, and all the participants, I thanks to them. Thank you, sir.
Thank you, Mr. Engineer Suresh Kumar. Thank you so much for an excellent vote of thanks. Now, I request all the participants, including the speaker, you can also fill the feedback form. You'll get the appreciation, that feedback certificate, the participation certificate. Apart from that, we will give you an appreciation certificate for Mr. Sanjay. That is different. Okay. Now, I request all the participants, whomever is interested in the certificate, they can fill the form, which will be shortly be posted. Now, it will be posted on the chat box. Okay. So, with the permission of Mr. Sanjay, I'll call upon the day. Thank you, Mr. Sanjay. We'll
Thank you.
keep
Thank
in
you very
touch, with
much.
sir. We'll do more programs in future, sir. We'll think
Sure.
of any programs in future. Thank you.
Thank you.
Thank you so much. Nice, very nice of you. It was a very good quality program today. Thank you so much for doing a excellent job today. Really, we enjoyed your show. Actually, it's a good knowledge treat on the CFD. We can say like that.
Thank
So
you.
I also exposed in DHL many of the CFD area. I worked in one BC and HRSC boilers.
Okay.
There I happened to learn something about the safety and all. And I also volunteer in that safety program, that 2 days program, national event. Really, it was, you reminded all the whatever is studied, you gave a touch. We had a very good touch today. Thank you so much. We are enriching our knowledge today. Thank you.
Sure. Thanks,
Okay, good
sir.
night, everyone.
Appreciate it.
Bye. Take care. Thank you. We'll keep in touch.
Yes, sir. Sure, sir.
Yeah. And Mr. Rajesh and Marimuthu, please post the feedback form on the chat box.
Okay, sir. I will send it, sir.
Yeah. Please post it. Please post it. We'll wait for another 15 minutes. People can fill that, this feedback form so that you will get the certificate in inbox. Within few minutes, you'll get the inbox. Kindly fill it. Kindly fill your name and your email and all carefully. Otherwise, if you mistake, it will not come to your inboxes. Rajesh Marimuthu. Hello? Rajesh Marimuthu.
Sir, சொல்லுங்க sir.
Yeah, another 5 minutes பார்த்துட்டு close பண்ணுங்க அவ்வளவுதான். Okay.
Okay sir. Okay sir.
Right, thank you.
Okay, thank you sir. Hello. I will close the program. Hello.